All right, the next section, day 9, section 3.5 talks about limits at infinity, and this is a little bit of a break from the curve sketching we were doing in previous sections. A little bit of a pre-calc review. The reciprocal function 1 over x approaches positive infinity near x equals 0 from the right side, negative infinity near x equals 0 from the left side. But if I want the limit as x approaches infinity, this function gets closer and closer and closer to 0, which is why we sometimes say 1 over x equals 0. It doesn't technically equal 0, it just approaches 0, so that limit is 0. That's true of any constant divided by x to some positive integer power up here, so that limit is going to be 0. What happens if you have something where the degrees are different? Well, the rule is that you go through and divide every single term by the largest degree. So since x squared is the largest degree, I'm going to take every term and divide it by x squared. That simplifies down into this, and then we get to apply this limit rule again. 1 over x is 0, 1 over x squared is also 0, so that limit is 0. So the next case is going to use that idea of dividing by the largest degree again, but this is kind of a unique situation. The degree in the top is first, and the degree in the bottom is also first because you have an x squared, but it's under a square root, so the square root of x squared is x. So how do we test this one? Well, we're still going to divide by the largest degree, which is x, but we're going to have x look like two different forms. In the top, we're going to divide by x, so 6x over x and negative 5 over x. And in the bottom, we're going to divide by the square root of x squared. That way we can bring this x squared inside the square root function. But it has to be negative because the question says our x's are approaching negative infinity. So what we'd like to do is look at what happens to this function as we approach negative infinity over here. So the square root of x squared is positive. We want to guarantee that we're approaching on the negative side, so we slap a negative in front of that. And we'll talk about the other case after we're done with this problem. So top gets divided by x. That simplifies down into 6 minus 5 over x. The bottom, dividing by negative square root of x squared, now the x squared gets to come inside, so it's 3x squared over x squared and 2 over x squared. That reduces down to 3 plus 2 over x squared. Taking the limit as x gets huge but negative, 5 over x becomes 0, 2 over x squared becomes 0, and we're left with 6 over negative root 3. Rationalizes this, simplified as that, negative 2 root 3. To check it, you could type this into your calculator or in Desmos. And if I also graph some horizontal lines at 2 root 3 and negative 2 root 3, we can see that this function, as x approaches negative infinity, approaches negative 2 root 3. If the question had said, find the limit as x approaches positive infinity, then this square root of x squared term, we would use the positive version. So again, the difference is negative infinity means you need to make sure that this is negative. Positive infinity means you make sure this is positive. You might say, why didn't we put a negative in front of the x? Well, the x is already negative. But when I take that negative x and square it, and then take the square root, that produces a positive number, so I need this extra negative to turn it back into a negative. Okay, for the next 3 examples, I'll walk you through the first one, and then you're going to try the second and third. So the rule for each of these limits as x approaches infinity is still divide by the largest degree. Largest degree here is x squared. Largest degree in the second one is x to the 3 halves, and largest degree in the third one, you're comparing x to the 3 halves to x to the 1 half, so you're going to divide by x to the 3 halves. Anyway, dividing each term by x squared simplifies into this. As x gets huge, 5 over the square root of a very large number is essentially 0. This is essentially 0. You get 0 over 4, which is 0. So take the second one, divide every term by x to the 3 halves, and you should pause the video, and I'll reveal the answer in a second. So here's the answer. Divide by x to the 3 halves, divided by x to the 3 halves, x to the 3 halves. 5 in the numerator, 4 in the denominator, 1 over x to the 3 halves. As x gets huge, when you square root it but then cube it, it still becomes a very large number in the denominator, so that's 0. Final answer is 5/4. Go ahead and try the third one. Divide every term by x to the 3 halves. So if you divide everything by x to the 3 halves, you get that statement. Reducing, you get this, which doesn't seem to help a whole lot. Now you're dividing by 0, and that's what's called an indeterminate form. We don't know what happens. So this is an example of something that is either a slant asymptote, and you can find the behavior by doing long division. We'll come back to this again a little bit later, but what's happening in this spot here is that since the numerator degree is 1.5, and since the denominator degree is 1/2, the numerator is larger than the denominator, which means you're going to wind up with some sort of a slant asymptote. You may remember how to do that from pre-calc. The next three screens will show pictures of these three plots. The first answer was 0, second answer was 5/4, and the final answer was a slant asymptote in the shape of, I believe, a linear function. We look at that plot. Here's the answer to the first one. We can see that this one will approach 0 as x gets huge. Plot of the first function does approach 0 as x gets large. Answer to the second one, we can see that this plot approaches 5/4. Plot of the second function does approach 5/4 as x gets large. And plot of the third function, if you do long division, you're basically taking x to the 3/2 and dividing by x to the 1/2, subtract the exponents, and you wind up with x to the 2/2, which is x to the first. So it's not a surprise that the slant asymptote looks like a straight line with a positive slope. So for a final example, to put everything together, we're going to sketch the graph of this function, and the directions say use extrema, intercepts, asymptotes, and symmetry. So the first thing we're going to do is do our pre-calc work, which is find roots and asymptotes. Factoring, we have a root at +1, and we also have a hole at -1 because the same factor cancels out at the top and the bottom. We have a vertical asymptote at 2, and you could plug in 0 for x and find the y-intercept, and plug in 0 for y to find the x-intercept. Well, we already found the x-intercept, the root of 1. All of that together is this. Intercepts at 1, y-intercept -3/2, vertical asymptote at x equals 2, and if you let x get large in this version here, as if you divide everything through by x squared, you wind up with a result of -3 as your horizontal asymptote. The next step is to find extrema, so you're going to take the first derivative of this reduced function and try and find maxes and mins. I turned it into, you could do the quotient rule, but I turned it into 3, 1 minus x, x minus 2 to the -1, doing the product rule, and then factoring out the smallest exponent. You wind up with that. Find the critical numbers, test them. At x equals 2, the first derivative is positive. Sorry, the first derivative is always positive. There's a critical number at x equals 2. It's always positive because 3 is positive and the denominator squared is always positive. So you know that your function is always increasing and that there are no extrema. Last step is to take the second derivative. You wind up with this statement down here. Means there's a possible point of inflection at x equals 2. When you take x equals 2 and do test numbers on either side of that in the second derivative, plugging 0 in the second derivative produces a positive. Plugging 3 into the second derivative produces a negative. So there is a point of inflection at 2. So now your job is to take all this information, put it on a graph, and come up with the final sketch. Pause the video and try and produce the sketch of the final plot. So here we go. We have roots at 1 and -3/2. We have a hole at -1. I'm just going to write myself a little reminder that says there's a hole at -1. We have increasing everywhere, so I know that f prime is positive everywhere. So the function is going to always be increasing. And we have a concave up everywhere and a vertical asymptote at 2. So how do I draw something that's always increasing and through those 2 points? We also have to make sure we behave by the horizontal asymptote at -3, so I'll put that in. Down here and down here. So traveling through those 2 given points and approaching both the red and the blue asymptote is going to look something like this. I'm going to go back and demonstrate that there's a hole at -1 by changing this spot here into an open circle and erasing inside there. Nope, I didn't want to highlight, I wanted to erase. And that's not going to let me erase, so should be an open circle there. How do we finish? Well, we need to have the right side also be always increasing, It must approach both of these asymptotes, the red one and the blue one. It cannot cross the x-axis because that would be another root. And if you remember your behavior for vertical asymptotes, because the exponent in the denominator is odd right here, that means that the direction near your vertical asymptote need to be opposite directions. So if the left side is going up along the asymptote, the right side will be going down. So the final branch looks something like this. There. That's your final sketch.